Good morning, dear students. Today we shall take up unit number 4, two-dimensional problems. In two-dimensional problems, we see the finite element modeling with the CST elements. The expanded name of CST is constant strain triangle. The expanded name of CST is constant strain triangle. The CST element is also called as linear displacement element. Linear displacement triangle, we say LDT. We can say CST element or LDT element. Constant strain triangle is also called as linear displacement triangle. When the displacement is linear, strain is constant. Okay? Right. The displacements, traction and distributed body force values are functions of x and y in two-dimensional problems. In one-dimensional problem, displacement is a function of variable x. Strain is a function of variable x. Stress is a function of variable x. And the distributed force, traction, body force are also the functions of variable x. Whereas coming to two-dimensional problems, the displacements, traction and distributed forces are the functions of variables x and y. Therefore, we can express the displacement vector u, capital U, the displacement vector capital U as a function of two variables, say u and v, which are the functions of variables x and y. Here the displacement vector u has two components, u and v. And here u is the displacement that takes place in the direction of x. V is the displacement that takes place in the direction of y. Therefore, u is a function of variables x and y and v is a function of variables x and y. The reason is, if you consider a two-dimensional domain such as a rectangular plate of uniform thickness, loaded with a set of forces, say F1 and F2, right? F1 and F2. These forces are acting in the direction shown. This is theta 2 and this is theta 1. Now here this is a two-dimensional problem. In this case, if you consider a point, it displaces in the directions of x and also y. Here we consider a reference frame OXY to define the displacement that occurs in the domain. This point has displacements u and v. U takes place in the direction of x-axis and displacement v occurs in the direction of y. U is a function of variables x and y here and v is a function of variables x and y. Here what is capital U? Capital U is the resultant displacement. Capital U is the resultant displacement, which is the unknown displacement, which we get by the vector sum of small u and small v. Okay, where the small u and small v are the rectangular displacements. Okay, therefore the unknown displacement u we can express like this. Okay, now, so coming to the stresses and strains, sigma, because it is a two-dimensional problem, sigma, the stress matrix, is a column matrix having three components. What are they? Sigma x, sigma y and tau xy. Sigma x, sigma y and tau xy. It is a column matrix of size 3 by 1. And the corresponding strains are epsilon equals to, again, epsilon x, epsilon y and gamma xy. It is also a column matrix of size 3 by 1. Next, we have a body here, a body of uniform thickness. This is a body of uniform thickness. So where area of this body is capital E. Okay. Now, some part of this body on the surface is fixed like this. It is stationary. Some part of the surface at the boundary is fixed like this. Therefore, every point on this fixed surface cannot move. Hence, the displacement u is 0. The displacement u is 0. And what are its components? Its components are small u and small v. If you take any point here on this fixed surface, for which small u equals to 0 and small v is also equals to, small v also equals to 0. If you take any point on this fixed surface, small u equals to 0 and small v also equals to 0. Because the points on this fixed surface cannot move, cannot displace, right? Now, on this body, so we have applied this traction, right? We have applied the traction and the concentrated forces as shown, where Px and Py are the concentrated forces applied at point I in the domain, and T is the surface traction. How we specify this traction? We denote this traction by capital T, and the unit of this is the force distributed per unit area. Where this traction is applied on the surface of this object, on the surface of this object, where it is applied on the boundary, Okay. Now, if you consider a point specified by the coordinates x and y, this point displaces in the direction of x by u and it displaces in the direction of y, so v, right? Where oxy is the reference frame. So with respect to this reference frame, so we define the position of any point in this domain and the displacements u and v, next strains and stresses. Okay. So here T is the thickness of this object and Fx and Fy, they are the body force components per unit volume. Body force components per unit volume. Fx is the body force acting in the direction of x, right? Fy is the body force acting in the direction of y. They are defined as the body force per unit volume. Therefore, if you want the body force of this solid in the direction of x, we have to multiply Fx by the volume of this solid. If you want the body force of this solid in the direction of y, you have to multiply Fy by the volume of the solid. Okay. So here what type of forces we have considered? If you visualize carefully, traction, surface traction is considered. It is considered as the force per unit area where the surface traction is applied on the boundary surface. Right? Now, Px and Py are the concentrated forces applied at point I. Next, Fx and Fy are the body forces per unit volume acting in the directions of x and y. Okay. Now we define the body force and traction vector. The body force and traction vectors. Okay. Now F is the body force vector. It has two components, Fx and Fy. Therefore, the body force vector F is a column matrix having the elements Fx and Fy. Right? Now, the traction is denoted by capital T. The traction vector is also a column matrix having the elements Tx and Ty. Okay. If we go back and see again the figure, this is the surface traction. This you can resolve into two components, Tx and Ty. The surface traction, how it is applied? It is normal to the surface here. It is normal to the surface here. With respect to the established reference frame, T can be resolved into two components, Tx and Ty. So Tx is the traction acting in the direction of x and Ty is the traction acting in the direction of y. Right? So therefore, the traction vector we can write as a column vector with two elements, Tx and Ty. Now, as I said, F is the force per unit volume and traction T is the force per unit area. Therefore, for body force, for body force vector, the unit is a force per unit volume. We get the unit of force per unit volume, and similarly for traction, we get the force per unit area. Okay. So here, unit of Tx is force per unit area and unit of Ty is force per unit area. Here unit of Fx is force per unit volume and unit of Fy is force per unit volume. Now, once you define the displacement field, you can also determine the strains. How you write the strain matrix? Okay, we know that the matrix for strain epsilon, the matrix for strain epsilon, it is a column matrix, hence you can write it as the transpose of row matrix. What are its components? Its components are epsilon xx, epsilon yy and gamma xy, where epsilon xx and epsilon yy are the normal strains and gamma xy is the shear strain. Okay. The displacement field U, if you observe, it has two components, two rectangular components. What are they? U and V, which take place in the directions of x and y axis. Right? Now, so here the strain epsilon xx, how you define epsilon xx? We can define as d by dx of u. D by dx of u. Therefore, epsilon xx is, dou by dou x of u. Therefore, epsilon xx is dou by dou x of u. Next, coming to epsilon yy. Epsilon yy is dou by dou y of v. And coming to the shear strain gamma xy, it is dou by dou x of u plus dou by dou y of v. Right? Once again I tell you, epsilon xx, it is the normal strain which equals to dou by dou x of u, and epsilon yy, it is the normal strain which equals to dou by dou y of v, and gamma xy, it is the shear strain which equals to dou by dou x of u plus dou by dou y of v. So this is how we define the strain displacement relations. Strain displacement relations. Okay. So once you get the strain, you can write, the stress strain relations. The stress strain relations. We know that for two-dimensional problems, the stress strain relations, we can write considering the two-dimensional problem as the plane stress case or plane strain case. We can write the stress strain relations considering a two-dimensional problem as plane stress case or plane strain case. Right? Therefore, so when you represent, the stresses and strains for two-dimensional problems, when you represent the stresses and strains for two-dimensional problems, how you get the stress strain relations? When you write, you get sigma equals to d into epsilon, where sigma is a column matrix of size 3 by 1. A column matrix of size 3 by 1. Column matrix of size 3 by 1, which equals to the matrix D. What is its size? 3 by 3 into, again, epsilon, it is a column matrix of size 3 by 1. Okay? Right. How many equations we get therefore? 3 equations. So all the 3 equations are represented in matrix form like this, where D is the material matrix. Where D is the material matrix. Now, we see the finite element modeling. Finite element model. When the two-dimensional region is divided into straight-sided triangles, when the two-dimensional domain is divided into straight-sided triangles, okay, all the triangles possess the vertices. Therefore, the triangles meet at the vertices. Hence, when they meet at the vertices, each vertex we represent as the node. Each triangle is formed by 3 nodes, therefore it consists of 3 straight sides. Okay. Hence, we say this 3-noded triangle is a constant strain triangle, or you can say linear displacement triangle. Okay. It has straight sides. Now, we can visualize the finite element discretization here. Here we have a two-dimensional domain. The domain is defined with respect to the established reference frame OXY. Okay. Now observe carefully. The entire domain is discretized into several straight-sided triangles. All the triangles meet at common points known as nodes. Therefore, this is the node. This is the node. This is the node. This is the node. Okay. Now, elements are numbered. Say 1, 2, 3. They are encircled. Right? Therefore, if I write a number in a circle, it represents element number. Understand? This is the first element. I draw here separately. This is the first element, which has 3 nodes. 1, 2 and 3. Okay. The element number is encircled. Right? Now, each node has 2 degrees of freedom. Because it is a two-dimensional problem, each node has 2 degrees of freedom. If J denotes the node, Q2J minus 1 is the nodal displacement in the direction of x-axis, and Q2J is the nodal displacement in the direction of y-axis. This convention I follow. I put J equal to 1, then I get here Q1 and I get here Q2. right? If I put j equal to 2, if I take j equal to 2, then what I get here? I get q3 and here I get q4. This is how I specify the nodal displacements. Okay. If you observe, the entire domain is discretized into several straight-sided triangles. What are they? They are the constant strain triangles. You can say linear displacement triangles. Now, if you observe carefully near the boundary, right, there is some unfilled region between the boundary of the domain and the side of the element. Okay, right? Here also there is some unfilled region between the boundary of the domain and the side of the triangle, right? Now, to minimize this unfilled region, what you have to do? Near the boundary you have to take smaller triangles. When you do finite element modeling, you should minimize this unfilled region, then only you get better approximations, then only you get the values very closer to the exact solution. Right? How it is possible? When you take smaller elements near the boundary, then this unfilled region will be minimized. This is important point. Okay? Now, here the surface traction is applied. Right? Where? On the object here. Observe carefully. On some part of the boundary, the surface traction is applied. Okay? Now, this traction where you consider on the corresponding side of the triangle. You know, this is 13th element. This traction you cannot consider on this side. You can consider this traction on the corresponding side of the triangle near the boundary. And similarly here, this is also the surface traction applied on some part of the boundary of the solid. Where you can consider this traction on the corresponding side of the triangle near the boundary. And these two triangles, if you see, right, they do not, suffer from traction. And these triangles, you see, they do not suffer from traction. And here, this part, if you observe, this part is fixed. Hence, the points on this part cannot displace. Therefore, the displacement vector for every point on this fixed surface is equals to 0. Only other points in the domain can displace when the solid is subjected to several forces. Okay. This is how we do finite element modeling. Clear? Next. The elements fill the entire region except a small region at the boundary that I told you. This unfilled region exists for the corner boundaries and it can be reduced by choosing smaller elements. Right? Next. The idea of finite method is to solve the continuous problem approximately, and this unfilled region contributes to some part of this approximation. Okay. Next. In two-dimensional problems, each node is permitted to displace in the directions of x and y, as I said, and each node has 2 degrees of freedom. Each node has 2 degrees of freedom. If you take a CST element like this, or linear displacement triangle, which has how many nodes? 3 nodes. Okay. Now, node 1 has 2 displacements. One in the direction of x-axis, the other one in the direction of y-axis. OXY is the global reference frame. Now, node 1 displaces in the direction of x-axis like this. As I said, for denoting the displacements of the node, I use small letter q with corresponding subscript, say 1. Right? Whereas, when you want to locate or denote the nodal displacements of the domain, you have to use capital Q. This is our convention. Now, And what is the other displacement? Q2. I told you if J denotes the node, Q2J minus 1 is the displacement in the direction of x-axis, and Q2J is the displacement in the direction of y-axis. Right? This convention I follow. Therefore, for node 2, what are the displacements? Q3 and Q4. And for node 3, Q5 and Q6. This is how one can represent the nodal displacements in an element. Right? Each node therefore has how many degrees of freedom? 2 degrees of freedom. Each node has 2 degrees of freedom. Okay, as I told you, to denote the nodal displacements in the domain we use capital Q. If J denotes the node number, capital Q2J minus 1 is the displacement in the direction of x-axis, and Q2J the displacement in the direction of y-axis. Right? Now, once you define the nodal displacements of the domain, you can define the global displacement vector, capital Q. Capital Q we define as a column matrix. Column matrix with number of rows equal to the total number of degrees of freedom of the domain. With the number of rows equal to the total number of degrees of freedom of the domain. Right? And coming to, Qn, what is Qn here? Observe carefully. Qn is the number of degrees of N is the number of degrees of freedom of the domain. N is the number of degrees of freedom of the domain. Total number of degrees of freedom of the domain. Right? And Qn denotes therefore the degree of freedom that takes place in the direction of y-axis at the corresponding node. Qn denotes therefore the degree of freedom that takes place in the direction of y-axis at the corresponding node. Okay, now we have a CST element here, isolated from the domain with 3 nodes, 1, 2 and 3. As I told you, Q1 and Q2 are the degrees of freedom at node 1 in the directions of x and y axis, and similarly you can visualize for the remaining 2 nodes, right, 2 and 3 also. Now we can define the element displacement vector. Element displacement vector we denote by letter small q, which is also a column matrix. Having the elements Q1, Q2, Q3, Q4, Q5 and Q6. This is how we define. Therefore, what is the size of this matrix? It is 6 by 1. For all the CST elements, we define the element displacement vector like this. Right? It is a column matrix having the elements Q1, Q2, Q3, Q4, Q5 and Q6. Okay. Now, and coming to the connectivity of the nodes with the element, that is also very, very important. That I tell you, if you go back and see the finite element modeling, right? If you see here, the entire domain is described into several subdomains. What is the subdomain here? CST element. Now, we see here the entire domain as the assemblage of CST elements. Okay? For first element, what are the nodes? 1, 2 and 4. In this, which one is first node? I can take node 1 as the first node, node 4 as the second node and node 2 as the third node. Or I can choose like this: node 1 as the first node, node 2 as the second node, node 4 as the third node. That is my choice. Or I can choose node 4 as the first node, node 1 as the second node, node 2 as the third node. That is my interest. Therefore, element node connectivity details are very important. For each element, you have to define which one is the first node, which one is the second node, and which one is the third node. I say node 1 is the first node, node 2 is the third node, and node 4 is the second node. This is how I define for CST element 1. For CST element 2, I can define like this. Node 2 is the first node, and node 7 is the second node, node 4 is the third node. All these details you have to give before solving the problem, right? The details we say element node connectivity details. These are very important. Okay. Now, this is the element displacement vector we have already defined. And coming to the nodal coordinates of the element here. See, the first node is specified by the coordinates x1 and y1, where oxy is the global reference frame, remember. Therefore, node 1 is specified by its corresponding global coordinates x1 and y1. And similarly, node 2 is specified by its nodal coordinates x2, y2, and node 3 is specified by its nodal coordinates x3 and y3. If you take any point at the interior which is specified by the coordinates x and y, and its displacements are unknown, they are to be determined. What are the displacements? U and V, which we have to determine. Now, the unknown displacement field U has two variables, as I said. What are they? Say U, small u and small v. These are the rectangular components. U and V are the rectangular displacements, right? Now, U and V are the unknown displacements which we have to determine. To determine these unknown displacements, what we do is, we use the shape functions. Shape function is an interpolating polynomial. It is a polynomial that interpolates the nodal field variables with the unknown field variable. What is the unknown field variable here? That is capital U, which has two rectangular components, U and V. Therefore, the unknown field variables at any point in the CST element are U and V. U and V are determined using the shape functions N1, N2 and N3, right? These shape functions N1, N2 and N3 are the linear shape functions. They represent area coordinates. Okay, why they represent area coordinates, that we see in next class, right? Dear students, in this particular class, what we have discussed, we have known about the constant strain triangle. It is also called as a linear displacement triangle. It has 3 nodes and 3 straight sides. We have seen the finite element modeling of a 2-dimensional domain, and we have discussed about the element and node connectivity details. We have defined the element displacement vector, global displacement vector. We have seen the stress strain relations for 2D problems. The strain displacement relations also we have defined. Right? In next class, we discuss about the shape functions. Thank you. Thank you very much.